guys, this is Professor Janacek, and I want to go over some interesting theorems. Let's begin with the intermediate value theorem. Let's let f be a polynomial function. Now, if for a less than b, if f of a and f of b have opposite signs, then we know that there exists a c on that interval a from a to b such that f of c is equal to 0. What this means, so here we have our a function. It is polynomial, and it's defined from a to b. Notice a is less than b. Now, you'll also notice that f of a and f of b have opposite signs. F of a is negative, and f of b is positive. According to the intermediate value theorem, there must be some c in between those two that is equal to 0. In fact, we can see that right here. There is a c value, and if you look at that function value, f of c must be equal to 0. Now, this is really an algebraic topic, but it's interesting nonetheless. Let's now take a look at the extreme value theorem. Let's start by letting f be a continuous function on the closed interval ab. Then there must exist a c and a d in the interval ab such that f of c is the absolute minimum and f of d is the absolute maximum of f. So here we have a continuous function that is defined on the closed interval from a to b. So it turns out that there must be a c value and a d value in here such that f of c is the minimum and f of d is the maximum within that interval. Now, of course, these could have been turned around. C could have been greater than D. There is no distinction where C and D fall as long as they are on the interval A to B. Rolle's theorem is the next one I want to look at. Suppose f is a function such that f is continuous on the closed interval and f is differentiable on the open interval. And we also have that f of A is equal to f of B. According to Rolle's theorem, there exists a c such that, oh dear, that's wrong. Let's take a look at that. That should be that c is in between a and b. So c exists between a and b, and f prime of c is equal to 0. This one's actually really nice. So here we have a continuous function. It is also differentiable on that interval. And so what we're looking for is a c value in here such that the derivative at that value is 0. So you'll notice that point right there, if you take its derivative, it's going to look like that. Remember, the slope of the derivative, the slope of the tangent line is the derivative. So looking at that tangent line, we can see that its slope is equal to 0. And now for the mean value theorem, suppose f is a function such that f of x is continuous on the closed interval ab and f of x is also differentiable on the open interval from a to b. Then there exists, same problem here. This should actually be that c is between a and b. Now in this case, for the mean value theorem, it turns out that f prime of c is equal to f of b minus f of a over b minus a. So let's take a look at that. What this one is saying, if we look at our graph, it is again continuous and differentiable. Now a and b do not have to be equal like we had in Rolle's theorem. But what's going to happen here is if we take a look at the secant line, turns out there's going to be a c value somewhere in here think it's going to be right around there, some c value, such that if we take a look at the slope of the tangent line at that point, those slopes are equal. So the slope of the secant line is going to be equal to the slope of the tangent line. In other words, they are parallel. There's a few more things that we can add to this, very interesting things. Notice that we're talking about, like I've said before, this is the slope of the tangent line. And this one here is the slope of the secant line. Turns out there is a point where they are equal. The other way you can think of this is that there is a point where the instantaneous rate of change is equal to the average rate of change. Now, the mean value theorem doesn't tell us exactly where that c value is, so I don't know exactly what c is, but I know that it's in there somewhere. Also, it does look like Rolle's theorem is a special condition of a special case of the mean value theorem. However, we typically use Rolle's theorem to prove the mean value theorem. So we prove Rolle's theorem first, and then we'll use that to prove the mean value theorem just by an extension. However, it does look like Rolle's theorem is just a special case of the mean value theorem. Let me talk a little bit about an example. Suppose we drive from Houston to Austin. Now this takes us let's say 3 hours. And we travel 165 miles. So what is the average speed here? Well, our average speed, and if we're looking at it in terms of the formula, that would be 165 minus 0 over 3 minus 0. So our starting time and our starting distance is 0. But we end up with the average speed again, miles per hour, 165 minus 0 miles divided by 3 minus 0 miles. So we get 165, not miles, that's hours. Whoops, there we go. So 165 miles over 3 hours. We can do that division. What do we end up with? Oh, that's what, 55 miles per hour. All right, what about the instantaneous speed? Well, I do know that it's probably true that we're not going to be driving 55 the entire time. At some point, we may have to stop for a stop sign or a red light. And at some point, as we're driving out there on the highway, we're probably going to go a little faster than 55 miles an hour. The stated speed limit is probably 70 or 75 throughout that journey. However, I do know that the instantaneous speed will specifically look at car mean the speed there is 55 miles per hour, as stated on the sign as you drive through. So that means the instantaneous speed is equal to the average speed. And there we go. They're just a few interesting theorems. Enjoy!